Hi, I'm excited to present our CVPR 2020 paper, When2com, Multi-Agent Perception via Communication and Graph Grouping. This work was done at the Robotics, Perception, and Learning Lab at Georgia Tech. In recent years, we have seen some great progress in applying deep learning models on different computer vision and perception tasks, such as image segmentation, depth estimation, and object detection. These models are mostly based on a single agent, which means that the input to the model is from a single perspective. However, single-agent perception is more likely to suffer from problems such as occlusion or sensor noise. For example, if a robot perceives the environment from a single viewpoint, there might be several blind spots. Similarly, if there are sensor degradations, the robot would have difficulty performing its underlying perception task. On the other hand, we also see the development of multi-robot or multi-agent systems, which can improve robustness to such failures. We therefore look at the problem of multi-agent communication to gain such robustness. Prior work in this area have looked at heuristic or hand-tuned rules for determining who to communicate with and what information to transmit. While learnable communication methods have been developed for other domains such as game playing, they often do not incorporate bandwidth usage. Instead, all agents communicate with all other agents at all times via high bandwidth information, regardless of whether it's necessary. Therefore, we're interested in building a multi-agent perception system where each agent can learn to communicate for solving perception tasks. Our goal is to maximize the accuracy of such perception tasks, while at the same time minimize the bandwidth usage during communication. We therefore formulate the problem as learning when, with whom, and what to communicate, all using the same framework. The high-level idea of our proposed method is as follows. Suppose that a person requires some information from the perspective of others. It can therefore request such information, indicating what information is necessary. The other people can then determine whether they have information that could be relevant. If one person determines that its information is relevant, it can then send it to the querying agent. Our idea is therefore to reduce the network complexity during communication. Rather than having every agent communicate with every other agent at all times, what we have is a handshake mechanism that determines whether communication is even necessary, and if it is, what information to transmit and who to communicate with. To this end, we propose a multi-stage communication framework within deep learning. It consists of 3 different stages. In the request stage, an agent sends a compact query to all the other agents. The key is that this query is extremely small, and therefore the bandwidth usage it uses is extremely limited. During the matching stage, all the other agents use this query to determine whether they have information that could be relevant. During the connect stage, the querying agent incorporates information that it received from those that had relevant information into its own local observations and performs the underlying perception tasks, such as image segmentation. We collect a multi-view semantic segmentation dataset, which is built upon the AirSim simulator. In the dataset, a group of 5 drones fly over a map with diverse landscapes, and we record the RGB image, depth map, pose, and semantic segmentation mask for each agent. We plan on releasing this dataset in order to allow other researchers to explore similar problems. We demonstrate the effectiveness of our proposed method on these 2 tasks. The first is the AirSim dataset that I just described, where we show that the accuracy and bandwidth usage beats all current state-of-the-art in distributed and centralized methods. Similarly, we show in a multi-agent 3D shape recognition that our method is able to both increase accuracy and reduce bandwidth usage. There are several exciting applications to our multi-agent communication work. For example, multi-robot systems that perform search and rescue, vehicle-to-vehicle communication in self-driving cars, or communication across multiplayer games to devise strategies. If you're interested in our work, please check out our project page and our CVPR talk. Thank you.